For those of you who don't know me, my daughter was born in Lincoln, and one of the famous things in the Lincoln Cathedral is the imp, which you can see in front of you. So that's why I've used that as a motto for this ongoing saga of Imp77. So, bit of a chat about one. I was hoping that some people would actually sort of go and grab the information on the GitHub, so they could also sort of do things at the same time. So, just in case, after that, I'll talk about the framework, and then discuss one of the core elements. One of the glue things is the I code. There's another glue component called the IBJ format, but I'm not going to talk about that today. Then I'll talk about what enhancements I have done and what I would like to do. And then, of course, a dreaded demonstration. So, first of all, let's go and get the compiler. It's available on the GitHub Silicon Sam, which is my nickname for some reason, and it's Imp2022. There's a README to go with that, which indicates basically you need to have on a Linux box. You need obviously the GCC compiler, but also it'd be useful if you had the free Pascal compiler loaded on as well, because some of the utilities I've done are built using that. There's inside that repository, there's a doc folder which gives you information about the I code and the IBJ formats, as well as currently you should have the 2 slide sets as well. It also contains the dreaded updated compiler and its source. So if you want to do that, you can go to the GitHub repository, grab the information using the code tab to download a zip file of the stuff. There's no need to bother about getting a duplicate of the repository. If you do that, then you can make sure you update your environments. Also, you need DOS to Unix, and because it's going to be done is 32-bit code, make sure you've got the GCC multilib installed, and as well as the FPC, the free Pascal compiler. So that's the blurb about how to get the actual compiler on your machine. So if you do that, load it onto your machine, go into the pass3 folder. So that will contain the program to take an IBJ file and convert it into ELF or COF format object files. So you need to do that first, then the lib folder, and run make bootstrap to actually build the library, the runtime library, and then the compiler itself in the compiler folder, again bootstrap. And at that point, you should have a working imp compiler. So what's the framework of the compiler itself once you've got it? It's got, as I say, 3 phases or passes, but 4 programs to be involved. Each pass is a separate program. The additional program is used to generate the parse tables from an Imp77 grammar. And that additional program is called take-on, where you just feed in the grammar and output the tables. So that is, as it were, the zero, the prequel to the 3 parts of the compiler. Part 1 is the imp source analyzer, which basically uses the parse and lexical and parse tables generated by the take-on, and then it generates the I code by using some of the information in the standard permanent routines file, and of course your imp source file to generate that ICD file, which is a binary format, and also a corresponding listing file. So if you make any mistake in the imp code, the listing file will help you at least try and find out what's gone wrong. Second part of the three-part compiler is pass2, which reads that I-code data and uses it to generate corresponding machine code, and then outputting these IBJ files. As I say, the caveat is only 32-bit code at the moment for Intel. I have dreams and visions of extending it a bit more, but I'll describe those later. Then, of course, the last phase, phase 3, is where it takes the IBJ files and converts those into object code for use either on the Linux or on the Windows box. If you use pass3coff, it takes the same, the IBJ, to convert into coff object format. Pass3elf will convert that identical object file, IBJ file, and creates the elf file. So use it to go target program either on Windows or on Linux. And what other components are there? There's the library code, which is almost all written in Imp77. There is some embedded Intel 386 assembler code used inside it to do the dirty things that Imp actually couldn't really work with. There's only one C file used inside the library, and that is accessing the C file IO. And of course, you then link your object files to the library for running. But as I say, just to repeat, the take-on program takes the grammar, generates the tables, and also other debug information. It could be used for generating tables for other languages, and has been in the past, but we don't have those language grammars around. So if you want to run it, you can see that. You can see how to invoke the command. So pass1, this is just repeatedly showing you again the routines with your actual imp source going into the pass1 and then out as a listing file and the hidden I-code file. Pass2, again, written in Imp77. The source is common to both Windows and Linux, and again, assumes the target is Intel, 32-bit. There are versions, as I said, for pass2 for other machines, but we don't have the executables available, except for VAX VMS, which is up and running running under SimH, and there's an old version for RISC-OS for ARM. But it depends on the format of the intermediate code of the IBJ of the I code, which is generated from pass1. So there may have been different enhancements and different I code parameters sent and provided by these old compilers. Again, this is how you run it through pass2, and then it takes in the first, as it were, glue file, the I code file, and then generates the other glue file, the IBJ format. I'll show some of these formats later. Pass3, again, to reiterate, it takes the intermediate IBJ file and creates the actual object file. But there are two versions, as I say, one for coff and one for elf. Both have been implemented in C, but I also did a scribbled an IBJ to COF program in 3 Pascal, and it seems to work. So I've got to sort of make sure that the Imp versions, the C versions that work are still consistent with the 3 Pascal version. Whoops. So there it is. Pass3 takes the IBJ and generates the COF or ELF file. I mentioned earlier there are some extra utility tools. One is called the ICD to assemble. So as I've said here, it reads the binary format ICD or ICode file and generates a textual version, and then reversing it back takes that textual version and creates the genuine binary ICD back. Then there's also IBJ to assemble and assemble to IBJ. So they take that pseudo IBJ file, and one creates the text and the other takes the text, converts it back to the IBJ file. And of course, they've got the IBJ to COF, which I mentioned. There's also a COF to dump, which is similar to dump bin from Windows. All of these are in Pascal, which some might say is another retrograde language. Finally, another utility I've just recently scribbled is one that reads the IBJ file, and there are excess IBJ records inside the file. For example, some records are a hangover from the standard permanent routines, and they go through. They're referencing external symbols or routines, but they're not actually used by that particular IBJ file. So it'll remove those and also compress some of the code as well. Next. This is where we sort of really start to get inside the compiler. This is for the pass2 phase, where what's ICode? What's it like? Well, I've done a document to try and describe the ICode instructions, which is in the document folder of the repository. And just the various sort of types of ICode instructions. One to access variables, one to do assignment of variables, some to indicate the block structure and calling structure, extra ones to help guide the compiler to generate extra debug information. Then there's the way of embedding machine code in the Imp source for those routines for those occasions really where you can't do it in Imp, but you do need the power of the extra instructions. Of course, jumps and labels to say, right, okay, let's move around the structure of the source code. You've then got to parameter and struct variable declarations, and then stack operations. And we'll show some of these in a bit more detail. The ICode interpreter, which is the core of pass2, uses 3 stacks. It uses a symbol table stack, which is used to store the symbol definitions like the variables, what type are they? Are they integer? What size integer are they, etc.? Or is this a routine call? And if it's a routine, is it something that returns a value, in which case it'd be counted as being a function. So routines and functions are, I'll describe them as similar. So if you want to declare a routine, there is an ICode for that. If you want to declare a variable, there's an ICode for that. and also for record formats. Now, this is a stack based, because one of the important things about Imp is you can have routines embedded within routines. That is, you can define a routine inside another routine. And that's why you have to have a symbol stack, so that as you're starting to define a new routine, which then defines another routine, effectively you're pushing routine definitions onto a stack. When you finish the definition of a routine, this will be popped. The definitions can be popped because they're not needed anymore. There's also another stack, which is for the variables, which are basically taken from the symbol table definitions. And as you're going through and using commands on the operation stack, like the add, subtract, multiply, whatever, this takes a copy and is used to indicate how you actually access a variable. Next, here's the actual I code which defines a routine or a variable or whatever. So the name, we've called it def, and it's got just a number of parameters. One, the n is a tag as a handle to access this particular definition. We also give the actual name of the symbol, and then we have a descriptor which says what type is this definition, is this name? Is it a function? Is it a routine? Is it a variable? What's the size of the variable, etc. The description of the def I code is also included inside that I code document I mentioned in the docs folder. So if you want to know a bit more about how a variable is described, refer to that document. As I mentioned, Imp allows nested procedures, which is like Pascal, but not C. So you could write an Imp program with a flat structure, like a C structure, but you'd have to then be careful about namespaces. So entry into the procedure pushes the new symbol table level, and when you exit the procedure definition, it'll pop that symbol table level, and that's how it makes sure that you only, if you have things with similar name, with the same name, the name might be nested inside a routine, but the name might be used later on. So you can avoid clashes that way. So the variable stack takes its data from the symbol stack, but you still reference a variable by its tag number, because you can then use that tag number against the symbol stack to get its type and size information. But you can also get the updated type and size information stored inside the variable stack. So these are used to basically form the instructions to access variable data. ASPAR is an I code instruction which takes, which is saying that the current variable is assigned parameter to a procedure. The top of the stack is passed as a next parameter to the second on the stack, and then top of stack removed, leaving second on stack as a new. We can show you later on. There's another thing called asval, which is basically assigning a value to a variable, where of course what value it is will have been defined and created earlier on before the asval instruction is invoked. And another one is a call, which is really a call to a procedure, and there are more in that set of I code instructions. Next, examples using the operation stack. There's push, where the parameter n is the tag which indicates which variable we're pushing onto the operation stack. Now, when we're saying doing a pushing a variable, it's a reference to the variable, but it does not necessarily mean we're creating the calculation at the time. It means that we are sort of saying, I'm going to be using this variable n, tag n, but I want to at some time allow it to be able to work out where it is going to be in memory, etc. Push I, oops, wrong one. Push I just pushes an integer value onto the stack, onto this really operation stack or instruction stack. So that means that if I was going to say the ask val, if I did a push I and then ask val, it says that that integer value is going to be assigned to that parameter. For pushing strings, push S. For sub, just subtract variables, and adding it. There are more variants. There's a sub A, which represents address calculations, and again add A, address calculations. There are more, as I said, they're inside the documentation for the I code. If I want to do control flow sequencing, I code line indicates what's the current line we're on for this imp source. Locate is for a label. So we're declaring a label at that point. There are actually two types of label definitions, one for user-defined and one for compiler-defined labels, and they have different keywords or different I codes. Forward says, I want you to generate code to jump forward to the corresponding label. Repeat, jump backwards. And then it's got obviously conditional jumps like jump branch if greater than, jump if less than, and all the another range of conditional jumps. So finally, we get an example of an I code sequence. Assume that the code, the int code, is this integer definition of Fred is equal to 4. And then we're going to be, we've already got a routine called Bilbo, which takes two parameters, obviously a string, and then an integer value. So the I code sequence would be define, for example, we'll call Fred as being tagged as num I because there's about 4 other definitions before us. We say Fred, and it's an integer. Then we're going to push the definition of Fred onto the stack, but we don't push, we push the tag on. Then, so we've got Fred on the stack here. Then we've got to push the value, the integer value 4, onto the stack, and then we can assign the value. So therefore we've got 4 has now been assigned into Fred. Now, another bit here. So Fred has been defined and has the integer value of 4. But now we're going to call up this Bilbo routine. So Bilbo will assume he's got tag number 2. So we're pushing 2. Then we're pushing this string, the variable name equals, and assign that as the first parameter. Then we're pushing tag number 4, which is it should have been 5 really there. Push integer 8. and do the command of add, and then assign the parameter, and then finally call Bilbo, because Bilbo should be this push 2 at this point. So that's an example I-code sequence. If you want to be able to actually see the I-code that's been generated from the imp source, if you've got the compiler, set up a shell variable called imp_diagnose equals 16 before compiling the code. That's a little signal inside. I remember I mentioned there were some compiler directives, that I-code compiler directives, and diagnose is one of them. So we're setting up the compiler to say, tag 16 means I'm going to have to feed certain values out. And I've used 16 to say, dump out I-code values. So on Linux, export, on Windows, set. And then the I-code will then be output in the cod listing. You need to use the FC, S, and I options on the shell script, which runs a compiler, e.g. Imp77 for Linux and Imp32 for Windows. I really ought to change the Windows shell script name, but hey, what the hell. So in both cases, this means basically retain all of the information, the intermediate files, and we'll then be able to see the I-code, the inside the cod listing generated by compiler for Bilbo will then show all the I-codes. Right. Another thing that's important for x86 and I-code. As I mentioned before, imp allows nested procedures, and the def I-code is where a procedure routine starts being defined. Now, Intel x86 has 2 special instructions to assist in nesting routines. One is the enter, when you're going into a routine, and one is leave, when you're leaving, where level indicates the nesting level of the actual sort of the routine. So if it's nesting level 3, so it's 3 deep inside a defined function, which then defines another function, which then defines another function, need to do that. It places additional storage space for pointers to the previous stack frames, which is critical. And it's used, it would be used for, if you were doing a Pascal compiler, it would need something similar. So you have to have the stack frames put into memory. Unfortunately, the maximum level allowed is 32, so you can only do 32 deep nested functions, which, if you've got something that's that complex, I think you need to rewrite it, the code. With leave, it's placed at the end of the routine definition, and it pops from the stack the however many levels of the pointers for the stack frames, and then you immediately follow it by a return. So this is critical. Imp uses these enter and leave for every routine. Standard call mechanism: push parameters onto the stack before invoking a call, pop the stack by size, by however many parameters and size of parameters. However, danger, imp pushes parameters onto the stack from left to right in the procedure call. So if you looked at this call here, for Bilbo, we put this value on, push it onto the stack first, then Fred, and then the 8, then sort of code to work out this second Fred plus 8 parameter. This is how imp does it. In C, you'd find the parameter for the value of Fred plus 8 would be first on the stack, and then the string, the pointer to the string, will be next. But imp does it first parameter, first on the stack, second parameter, second on the stack. So there we go with that. Now, what I've done is the imp compiler that we've got is assuming that the code is embedded in a C-based operating system environment. So we've got access to the OS environment, i.e. the program arguments and the shell variables. However, C strings are null terminated and could be longer than 255 characters. So the system routines, using the system, it uses the C calling standard, but we have to convert the strings from C format to IMP's format. So these are new library routines which are implemented inside the standard perm imp. So you can access the environment and your program parameters as needed inside an imp program. So what enhancements? Before I sort of started, Pass2 could know that there was an attempt at having an embedded piece of machine code, but did nothing with it. What I've done now is I've actually managed to get it to work to a certain extent, that you can embed machine code inside the compiler. Pass1, as I said, already allowed you to embed machine code, but Pass2 didn't do anything. So what did we have to do? We had to create an appropriate machine code assembler and then be able to insert that machine code into the output IBJ file stream. It's not 100% in the new Pass2, but it's getting there. Next, imp allowed 32-bit integers, but also had 16-bit integers. And the compiler cheated. It said, right, okay, you've defined a short integer, i.e. a 16-bit integer. I'll pretend it's a 32-bit integer and go from there. So of course, if you sort of meant to add two 16 bits, which would have gone over the 16-bit limit, the compiler didn't care, which was something that needed to be sorted. So I had to upgrade the various interpreter routines, and I had to also add in create instructions, which was helped by the fact I'd already was able to add in a machine code assembler. The imp runtime library did have a lot of C code at the time to for the access to, say, files or whatever. But what I've done now is I've done it, but there's one thing which accesses the main C files like standard in, standard out, etc. Those handles are still accessed via the only C routine inside the runtime library. Also added a capability so that you could read random access files, and that's been quite useful at times. So how do you embed machine code? Got two ways to do it. One is sort of running using it's like an assembler notation, where you've got the star says, oh, we're going into embedded machine code format, and then you define your instruction. Oops. So a move taking the contents of EAX register and put it into wherever the stack pointer offset by 8 is. Another example is I'm going to add 118 into EX. Sorry, I should make the point that this is basically using Intel layout in which the right-hand parameter is the source and the destination is the left-hand side. So we're actually I should say, you take the thing on the stack offset by 8 and the contents of that that points to, and put it in the EAX register. Store 118, or rather add 118 into the EAX register for this one. For MOVSX, basically take the AX register and sign extend it into the EAX register. You could put it into a different register like the EDX, etc. Other ways of embedding machine code, and this one is actually quite useful at times, is to say, okay, store this byte into the instruction stream, and this byte, so 0F goes first, BF goes next, and C0 goes next. And I'll explain later on why this has been useful to be able to store the actual individual bytes when I don't have the appropriate instruction defined. So, if you're going to embed instructions in this assembler notation, you need a parser to parse the assembler text. You need to recognize the instruction. Is it a valid instruction? And does it have the right number of parameters? And are these parameters legal for that instruction? So you then convert that assembler text to the actual binary instruction. You've got to recognize registers, addressing modes, and also values. And then there are problems like assembler directives. For example, the example before I gave was move sign, the Intel instruction, move the sign extend from of AX into EAX. First of all, is MOVX FX a legal instruction? And is that parameter sequence legal? And are these values legal registers? Well, of course they are, but the compiler has to check these things out. But embedding raw binary, it's just taking that binary digit, but it's normally in the range. Is it going to be in the range 0 to 255 or -128 to 127? Well, normally it would be the unsigned byte range, which is the 0 to 255. You've then got to go through and say, right, you should validate the sequence. Does it form a valid instruction for the instruction set? So you've got 0F, BF, and C0, which actually are the sequence to do that MOVSX, EAX, AX. So this is generally a useful mechanism to add code into the code stream if the assembler is missing certain instructions. Because at the time of writing, when I was trying to do the 16-bit integers, we did not have MOVSX defined. So it's now added and defined into the compiler. So what was required for getting 16 bits? As I've mentioned before, Imp77 can have 16-bit integers defined by the code text short integer. As I mentioned as well, the original compiler cheated. It implemented the short integer as an full integer. So you may say you're wanting 16 bits, but actually I'm going to give you 32 bits instead. Well, one, how do we implement it as a genuine 16-bit value? One, the imp grammar had to be tweaked to indicate that a short integer was actually 2 bytes in size. The original grammar had short integer is 4 bytes in size. You've got to make sure that the ICO def file remembers when it's interpreted, that is the ICO, the def ICO says, oh yeah, size is indeed 2 bytes. And then the long, hard struggle of going through and making sure that every arithmetic ICode instruction would generate, i.e. the add and sub, would generate appropriate code sequences for 16-bit values. And then you have more basically assignment codes to be 16-bit aware. And as you can see, I did have problems with stage 3 and stage 4. So, arithmetic operations, you've got to be careful about numeric overflow, underflow, which can be a problem for the add, subtract ICOdes. You need to do the assignment from 16-bit between 16-bit and 32-bit integers, which is a problem for the assign value instruction. So, what do you do? Obviously, you want a word location, that is a 16-bit location to store the 16-bit integer. Whenever you're going from a 16-bit into a 32-bit integer, use the movsx instruction. So you extend that, extend that integer. You can do all the 16-bit integer arithmetic as 32-bit arithmetic, so no change there. But you've got to check each 16-bit arithmetic operation to see if it goes out of range results. And then check that the assignment into 16-bit is in the 16-bit range. And signal an appropriate imp event. This is the error handling, bits of like the to indicate where something has happened, and it will be picked up later on by another piece of the source code. So, other problems. If you're passing 16-bit integers as a parameter or being returned as a function result. Danger. Parameters are passed on the stack for Intel. This is for the Intel x86, not for 64-bit. So it's a 32-bit set that uses the stack. And then the function results get passed back in the EAX register. However, Intel x86 only allow register to register and register to memory, and memory to memory is not allowed. But the stack pointer must be aligned on a 4-byte boundary. So if you try to stack a 16-bit integer, which takes 2 bytes, stack alignment problems. How do we solve it? As I said, as it's obvious before, pass the 16 bits as 32-bit values, use the movsx before stacking the parameter, and then, which of course extend it into a 32-bit integer, and then when you're going from the EAX register back to the place where it's to be stored from, as a result, you just take the AX register value. So you're getting rid of the top 16 bits. Right, potential enhancements. Oh dear. I'd like to write the pass-3 in Imp itself, um, because my belief is if you have a compiler, you should write the compiler in the language it's compiling. Unfortunately, um, this would probably cause problems in that, but this is to do with basically making sure the pass-3 version in C and the pass-3 version in Imp are consistent. They generate the same object files. And if you do any extensions, then make sure that extensions or changes to the code, to the pass-3 code base, is consistent across the two. One other thing I'd like to do eventually is to go from the 32-bit compiler, so the x86, to the 64-bit code. But we need to be able to have 64-bit integer types. So we already have byte integer, we have short integer, and integer or long integer as a paraphrase. So we probably need to have something like long integer for the 64 integer type. And the addresses would have to then also be 64 bits. But these could cause problems in Imp programs, the historic ones. Another thing I like to do is to create a version of pass-2 which would cope with ARM, so I could put it onto my Raspberry Pi setup. Thing I've also just recently purchased a RISC-V toy, so that would be another thing to play with. So there'd be quite a bit of work there. Right. I was going to go and now give a demonstration. I hope this is a reminder of if you wanted to follow this or put your Imp onto your Linux box, this is what you could do. If you look on the README for the Imp 2022 repository, this information should be there already. So I need to close this and right. Oh, as I mentioned, on the repository, there are two files that will give you details about the IBJ format and the ICode format. So if you want to look at those, there's also a brief documentation about the compiler implementation, which you might find of interest. Now, let's get to Right, what I'll try and do is show you getting the compiler built from the a zip file of the repository. So we'll go into a place where I've stored the Imp2022 code, and you'll see there a few of the folders, such as the
John, just you're still showing your slides. Not sure if you're expecting us to see.
Right. I'll stop that share, and then I'll have to go and get the where's the damn share screen? Yes. Right. Can you see this now?
Yes, I can. Thank you.
Right. So what I've done is earlier I took a copy of the repository as just a file. I didn't sort of duplicate the repository. I just took the code zip and then expanded it out. So what you've got here are the corresponding folders that you'd see inside the repository. So you've got the compiler, the docs folder, the lib folder, pass3 folder, etc., etc. I won't talk about the scripts folder because that's really mostly used for the Windows flavor. And then tests are, so you can use this. This has got some imp code which you can use to compile up and see if the compiler is working properly. But what we can do is, let's go and see if we can build the compiler up. So first of all, you go into the pass3 folder, and then, oh, I know what to, yes. I was getting a bit of a panic then. But all you can do is make bootstrap. I can spell it properly. We can ignore some of those errors because they're really talking about the version for auth. So what we should now have is the pass3 elf program compiled up, and also a pass3 coff program compiled up, running under Linux. So I could, if I wanted, generate coff object files from the IBJ files, but we're under Linux, so not bother. Next step, go to the lib file. Let's see what we've got here. Now you'll see here we've got imp files, and also usually a common IBJ file. Now the reason I've done that, I've stored the IBJ files inside the repository is so that all we need to do is run the pass3 over these files, and we'll have the corresponding object files, whether it's for Windows, for the coff object, or for here, Linux, the elf object files. And again, we just make bootstrap. Right. So that's inside the appropriate library. By the way, I store the imp compiler executables and any include files in the user local folder tree. Then, last step is to go to the compiler folder and bootstrap that. You'll have noticed that I'm using DOS to Unix to change some of the files, because since I do some work on Windows, I can never remember whether I've got the appropriate line ending set up. So that's why you need DOS to Unix for your thing. We've now got a compiler. So let's go and see if we can test out some of these programs. Let's go to tests. Right. Which should we do? Baggins or Bilbo? I think I'm going to try Bilbo. So, Imp77 minus FC FS FI on Bilbo.in. Right. So we've now compiled Bilbo. So try and run it. Oh dear. We've got a little problem. Because it's actually expecting a parameter. So what parameters shall we have? Files. Of course, what we should really do is to have a look at the actual source code. So let's have a now. What is it expecting? Expecting. Got a bit of debug there. So it's just expecting one output file because reading the imp source, it's got this one here. So, and by the way, getarg is the routine which gets the first program argument. Normally, an imp program would be sent to begin and then end, but you can define it as an actual routine by using this structure. But you have to call it, you have to use a thing called alias, and you have to call it imp main. And then it becomes, it's okay for program. So let's try what we've got there is a program has run. It's found it's got a count of 2 items, obviously the program name itself and the first parameter. And there's an environment count of about 28 environment variables already defined. So what shell am I using? There. It's under the Windows subsystem for Linux, blah, blah, blah. My computer name, the current working directory, who's am I logged in as, etc. And all of the other bits and pieces there. Now, I did mention before that we could show some of the I code. So let's first of all one day I'll learn how to type properly. Right, and let's have a look. I don't know if I can. I'm going to stop the sharing this one and try and get to see if I can get my complete screen. So right. Now, hope you can see the folder directory. And you should then see a file called bilbo.cod. which is the code listing file. And let's look at that. And what you see now here is all the iCode files, iCode instructions being shown. So, for example, one iCode I've not mentioned is called lang, which is only written out once at the very start, and it's there, I think, as a just in case you're going to write things other than Imp, maybe Pascal or whatever. And so 0 is for Imp77. You can see here we're defining tag 1, and it's going to be the rem function, and this stuff can be decoded to indicate. I've also printed out a decode saying it's a primitive integer function, which is a specification, and it's an indirect access, and it's to start to check. Now all of these things here, you start to define, and then you do a finish if it's a forward declaration. I'm just going to get rid of a lot of these things to make sure it's clear. And whoops. Right, so we've got at line 2 this imp code to say we're at line 2, and this is the imp source code, and this imp source code generates these iCode instructions, and then these iCode instructions then generate appropriate code like the enter command. So we're entering here with level 1. At line 3, we've got the definition of integers I, j, and max. So you can see defining I, j, and max. One thing to note, Imp always converts variable names into uppercase, so that if I wanted to link this program with or include routines from here in other machines, I'd have to use the alias command to make sure I get the appropriate lowercase name for the symbol. So you can see there now we're defining, in this case here, we're defining I, j, and max with the various values and typing information. I think that's about all that we can say for that one. Okay. Now, I go to this other folder. I've got an example here of 2 versions of Bilbo. As you can guess, I'm a fan of Tolkien. So, on the left-hand side, we've got the imp code. On the right-hand side, we've got the C code. And you can see it's close enough so that I'm defining a count, which in the C version will be assigned the value of 13. So that's like a global variable, global static variable. But in the imp version, I'm doing it as 42. X0, I'm zeroing the count. Xinc, I'm incrementing the count. Xdec, decrementing it. And X value, give me the value back. And you can see here, corresponding definition is to have the external and routine, etc. And this is where, although the routine I called it inside imp is 0 count, I've given it an alias of x0 so that I could, if I wanted, if I compile a program up to use the C version, if I created a compiler to run the imp version, there would actually be no effective difference because it would call the x0 in the lowercase, right? So what we can now do is go into this demo area. And myself, yeah. Let's compile the C version of Bilbo, and let's make it into a shareable library. So and then I'm going to build the Baggins program. Now, we have the C program, and we've got an Imp program, and Baggins is going to call some of the Imp C code. So if we run it, we'll get a result out, and the value it says is 23. So let's look at Baggins Bilbo.c starts a count at 13. What does Baggins do to that? All Baggins does, it says, oh, I'm going to use, I need these 4 routines, and I'm just going to call the increment. So at the start, it'll be whatever it was initialized to. In this case, would have been 13, and then do a for loop 10 times to increment it. So the value should be at the end, as we said. Right. As we can see, 10 plus the 13, 23. If we did the same thing with Imp, if you remember what the Imp value started out as, so if you can see the Imp value, 42. So we're going to increment it by 10, so it should come out as 52 or 53, if I remember rightly. So next step is to run the newly created Baggins. Yeah, 10 more than the 42. One last thing to do would be to look at the code file for just getting rid of all the excess code, because all they are is just defining the standard routines. We can just see what. So you can see here in this example, we're starting out with making a count 42. So push the value 42, define the count, initialize it, and we're at line 5. And then you can see here for the 0 count, push the definition for count. We're going to push 0 on and then assign the value. And there's the code for that. And that could be compared with the machine code generated from the C, where you can see, oh, we've got lots of extra bits and pieces inside, where this stuff is due with event handlers on the stack. So it actually isn't really needed. And we've also got this extra thing called global offset table. Now, a global offset table is used if you've got a shareable library, but it's referencing data. You don't want the data to be stored completely with the original library code. You want it to be stored slightly separately, and that's what the global offset table does. So the count is stored as an offset inside this global offset table, and I want to be able to convert the Imp compiler such that it can also handle shareable images in the same way. But that's for the next few minutes. Right, well, I think that's about all I have to say on the delights of the insides of the compiler. If you want to see all of the code examples again, that they are inside the Silicon Sam blah blah blah, and you can see tests going into tests. You can see the demo code as well. So if you want to play with that, you can do that by all means. I think I'll stop sharing the screen now. And
okay, so there are questions on the chat.
Yes, I've noticed. Right. For the problem about sadness trying to compile pass3, have you got the GCC multilib installed on your Linux?
Yes, actually, if you scroll down a bit, yes, I did. I fixed that.
Okay.
Before that, Adam was asking about floating point support.
Floating points? What are they? Yes, there are some floating points. It uses the floating point register that are embedded on the 386. And you can push numbers onto the stack and pop numbers out. And so you can do calculations with floating points. I've just not shown them.
Okay. And then, sorry, Adam's left now, so I'm asking his questions. So he asked, we had a question when you talk about nested functions, about scoping. So
yes.
So our names nested are all nested scopes searched?
Right. When you add a new definition to the stack, and you're then have a variable which may be in a higher level entry in the stack, it will basically sort of go from where I am now down to the first entry on the stack to search. Yeah. Mm-hmm. So that's the only way it will find out. If you're trying to have the same name, then how can you have the same name if you've got the name Fred stored inside a routine Joe and Fred inside a routine Joe called Bill? Then when you get to the definition for Joe, there'll be a thread available access inside that. But when you then exit the routine Joe, the variable, not the variable stack, the symbol stack gets popped. So you don't see that thread at all. You then get pushed down into the next routine, which has the thread variable inside it, and then you can see thread from that point. So that's how the scoping rules work. Is that clear?
Okay. Next question, also from Adam. It sounds like pick only. So I guess he's asking, is it position independent code only?
Yeah. Good question. I refuse to answer on the ground it may incriminate me.
Okay. In that case, you mentioned historic imp code. And
yes.
So is there a library of such historic imp?
Oh, yes, there is. Oh, yes. Sorry, I need to go back to let me look at my slides. I'll try and put this in here. But you can see this. The slides are also available inside the repository and the GitHub repository, so you can see some of this information that you've already got there. And I think the bottom line is go to history DCS ed ac UK/archive, and then look down there inside that folder tree, that web folder tree. And there are bits and pieces there. One thing I didn't mention was, well, I did mention that Imp was used as an implementation language, and it did implement a system called EMAS, which stood for Edinburgh Multi-Access System. And that was used by Edinburgh for quite a long time, and even got far south as Kent, where Bob Eager used to support it then, and he gave a talk about EMAS from the BCS. So I don't know if I mentioned that quite a while back that he was giving this talk. So yeah, and then if you've got SimH available, you can try the Imp compiler for that on the VAX. If you have a VAX flavor, well, if you have if you have SimH running a VAX flavor, you can get the compiler there. And I think that's about it for that question. Any others?
I think Phil had one.
Phil, we will store stack parameters in the way that we want, and not how C does it. If that's the question.
I guess maybe the deeper question is, apart from that, not wishing to do the same as C, is that part of the Imp standard, the way the stack?
It is part of the Imp standard, and I think Imp came before C anyway. So C as a parvenu can do things the way it wants. I think it's just a case of, oh, we've got a parameter. This is the first parameter, so we'll put it on the stack first, and it makes the code it really sort of follows the Imp I code, making it easier to follow. It's just that I don't know, but of course you have to then, because it's on a stack, you have to sort of have bigger numbers to access the lower entries on the lower parameters. you know, when you're using talk about getting the frame pointer, getting your value from the parameter from the stack, first parameter will be furthest away from where you currently are on the stack. Assuming the stack's built going from the top values going downwards. Yeah.
Okay, that's all the questions from the chat. Anyone have any more? I see that Chris did manage to compile the compiler during the talk. I'm having a bit of problem with the compiler, but I think that's mostly because I've been awkward and not decided to put it in user local, and I've been hacking your makefile of it. And I think that's messed up in the library search path.
The other thing as well is there is a loader script that goes with it gets installed from the pass3 build stage, and that is assuming that you've got the 30-bit environment, and also it will be pointing to make sure that you are looking in the user local environment for imp details.